Alright, so we'll continue on with where we were in 8.3 and we'll see how far we get. So up next we have the fifth root of 486. Now this one, and you can see I kind of moved the page, but that's because I needed to think about what are perfect fifths that could fit inside of 486. So 2 to the fifth is 32. And if you tried to divide 32 cleanly into 486, I'm pretty sure it doesn't work out. I should know that already, but I don't because I'm doing this with you. So let's confirm. 486 divided by 32. Yep, it does not work out cleanly, so that must not be our perfect fifth, if there even is one. There might not be. But let's look at 3 to the fifth. 3 to the fifth, remember, is, I'm pretty sure, 243. Now, 243, when I look at 46, I can see that that's times 2. So I've now found my perfect fifth, 243, and I found the 2 that's left over. Okay, so I've got to start to my answer. My answer is going to be 3 on the outside because I was able to take that perfect fifth root, and I'm left with a fifth root of 2, right, the other part left inside. So 243 can fifth root, it turns into 3, and 2 is trapped inside the fifth root. Okay, from there, let's continue on with our mixed number approach. We have 11 over 5 for the x's. We have 14 over 5 for the y's. So for 11 over 5, remember that as a mixed number, that's 2 and 1/5 if you convert that into a mixed number. So that means I've got 2 x's on the outside and 1 x left on the inside. 2 and 1 in my fifth root. And then for 14 over 5, that's going to be 2 and 4/5. So 2 y's on the outside and 4 y's inside the fifth root. And so that would be my answer. All right. So you can see it gets a little nasty, but always remember the mixed number approach. Turn those improper fractions into mixed numbers. How many times can 5 go into 11? Twice with 1 left over. How many times can 5 go into 14? Twice with 4 left over. All right, and let's continue. For this next example, what I'm going to do is, once again, I'm going to multiply before I deal with any square rooting. So what I mean by that is my first step's going to say, well, 4 times 5 is 20. And then I've got the square root of, let's see here, 5 times 50, which is 250. And then x to the fifth times x to the fourth would be x to the ninth for everything we've said before. So I now have, in 1 minute, sorry, I'm going to see if that just gets a little bit rid of the shadow. Anyways, so again, we're doing when our exponents are, when our bases are multiplying, our exponents are adding. So we now have x to the ninth inside my square root. Okay, well, what do we do from there? Well, there's going to be a 20 that's going to tag along. When I look at 250, I think 25 and 10 in terms of squares. There's my perfect square. There's the leftover. 10 doesn't break down into anything that has a square. And then, of course, I've got 9 over 2, which, again, we'll deal with as a mixed number, which would be 4 and 1/2. So for this example, let's see what I have. I've got the 20 from before. So I'm just underlining it to kind of say there it was, there it is. Up next, with the 25 being square rooted, that's going to turn into 5. I need a square root over here for the 10 that's left. Then for my mixed number, again, 9 over 2 is 4, so x to the fourth, and 1/2, so 1x inside my half root. And to clean that up, that means I have 100 x to the fourth root 10x. And that's as simple as it gets, but that's what we need. All right, and just one more. We've got division up first, so we'll review our division rules. Well, 9 over 3, that's just 3 with our coefficients. If I've got 2 square roots dividing, I can just divide their inside contents. It turns out that 245 divided by 5 ends up being 49. And then z to the ninth over z to the fifth ends up being z to the fourth. And b to the sixth over b is b to the fifth. And if we once again think about our mixed number approach, that's 4 over 2, that's 5 over 2. Now watch what happens here, and I'll underline my 3 once again just to say here's the 3 from before. And so square root 49 is going to be 7. So that's freed up from the root, and there's nothing left over. z to the fourth, or in other words, look at my mixed number, 4 over 2 is just 2, and there's no remainder. So far, I don't need to write a root. Why don't I need to write a root so far? Because, again, 49 rooted nicely, 4 over 2 divided cleanly. But now let's look at 5 over 2. 5 over 2 is 2 and 1/2, so 1b left inside my root. Whoops, so sorry, that should be 21. Z squared, b squared, square root b. Goodness. All right, just make sure you end up multiplying that 3 times 7. Okay, that honestly to me is kind of the harder part of the section. Let's move on now and get to some of the easier parts because these are a lot simpler. Now, the main idea in this section is to remember that not only now when we're adding and subtracting do we need similar types of roots, but we actually need like exact matching roots. So in other words, if you can say I've got 6 of something and 3 of something, then I have 9 of something. That sounds very informal, but that's the way we're going to approach these problems is when we're adding or subtracting, I need exact matches, right? So I can't even get away with, let's see where it was on a prior example. We'll find it here somewhere. I know I'm flipping through. My apologies. But let's see here. So for instance, right, this question right here, if there was a plus sign in between these two, or even if there was a plus sign in between these two, I really couldn't do anything, even though they're both cube roots. So when you're adding or subtracting, they need to match precisely, is what we kind of wrote down in the general notes that, again, we'll have where we outline the rules. So in this example, though, to follow that logic, I've got 7 of this very ugly thing, but I also have negative 12 of that same very ugly thing. And so then I have negative 5, 7 minus 12 of those very ugly things. And that's all that's going on there. All right, so then what happens on the next example is we start looking for like terms, essentially. I have 14 of this and negative 5 of this, so I have 9 of that. But then, I'm using a different kind of underline. Then I have my root 11s. There's a negative 1 and a positive 2, so I'm left with positive 1, which I don't need to write the 1 in front. Positive 1 of my root 11, and I'm good to go. All right, now what does that mean for the next two? For the next two, it makes it seem like, well, we're done. There's nothing to do because those aren't the same type of root. But let's look at our 3 prior examples. 7 can't be broken down at all. 5 can't be broken down at all. 5 or 11 can't be broken down at all. But 28 can be broken down into a perfect square of 4 with a remainder of 7. So guess what that means? We have 2 root 7 and an additional square root of 7. So now I have 2 roots of 7 and 1 more root of 7, so I have 3 roots of 7. So be careful. The reason the last 3 went by so quickly is because I knew the inside contents could not be simplified further. But if it can be, don't be quick to say, oh, these don't combine, I'm moving on because I don't see an exact match. You need to start asking yourself, is there a perfect square or, in this example, a perfect cube that I can deal with? So let's deal with that perfect cube. For this one, when I look at my perfect cubes, once again, I'm going to think what numbers could go inside. And so let's see here. 2 cubed is 8, but 8 won't go into an odd number. 3 cubed is 27 again. And 27 I actually think goes in, and you actually are left with a remainder of 5, which is good because we had a remainder of 5 essentially in this other problem. So what happens here? We've got 4 times 3 from the root of 27, cube root 5, minus 2 cube roots of 5. And so I'm going to do this kind of quick, but that's 12 of these things minus 2 of these things. So we have 10 cube roots of 5 when this is all said and done. All right, so the bigger caution here is, although most of those examples are easy, be careful. They're only easy if you know that your roots are, I don't want to say reduced, but maybe that is kind of the word I'm going to use. Like, make sure you've taken any perfect square you can out of your root and then check if they can combine. because that's what happened on the last two. All right, now we get to multiplying radicals, and this will feed us into further questions. Now, all we need to do is just FOIL here. And let's see what happens when we multiply radicals. Well, we've actually done this a lot. It just might not feel like it. But let's see what happens. 4 times 1 on the outside is 4. 5 times 5 on the inside is root 25. And I know you're probably thinking, oh, a root and a root multiplies and cancels, but notice that I'm going to cautiously write out what it is before I quote-unquote cancel it and just get 5. Let's keep going, though, and here's why I'm not going to do that, to show you what happens when they aren't perfect matches. Well, 4 times negative 5 is negative 20 on the outside. On the inside, a 5 times a 2 will end up being a root 10. So we've seen this a lot in earlier examples, but when two roots are the same type and they're multiplying, you can just multiply their insides and outsides together, right? 4 and negative 5 make negative 20, and 5 and positive 2 make positive 10, and that's happening in the root and outside the root. So let's see what happens. Root 2 times root 5 is just a positive root 10, and a 1 out front because they both had 1s, or in other words, an invisible 1. And then an invisible 1 times a negative 5 root 2, that's going to be a negative 5, and then root 4, because 2 and 2 make 4 when you multiply them on the inside of the root. Okay, so what happens now? Well, this is 4 times just 5. Now here in the middle, this is going to be negative 19 roots of 10, because there was negative 20 and then a positive 1. And here, this is negative 5 times 2. And if you work that out, just for sake of time, I'm going to call that 10 minus 19 roots of 10. So what happened there in that last step is this is positive 20, this is negative 10, and that does make positive 10 at the end. So when we FOIL, or when we multiply, remember the inside contents of matching roots, so square root, they will multiply and then deal with them afterwards. Don't be too cautious to say they cancel, and we'll see why in this section. So in this next section, we're going to be talking about rationalizing. Now, what rationalizing refers to is the fact that square roots should not be in the denominator of your final answer. So again, the problem is that if there's a square root in the denominator of your simplified or supposedly simplified form, well, then it's not fully simplified, is kind of what we're saying. So what am I going to do about this? There's a root 5 on the bottom. Well, the best thing I can do is multiply root 5 over root 5. What will that do? That will give me 8 root 5 over root 25, because the inside contents can multiply because it's the same type of root. What does that do for me? Well, that gives me 8 root 5 over just 5, and now I have rationalized. So that's a big topic that shows up in some later courses. Honestly, you probably won't see it too often until you take maybe trigonometry or pre-cal. And if you don't, then great, you're free. But for the moment, the idea is we need to get rid of square roots in the denominator, or we need to get rid of any nth roots in a denominator. And so let me say the general strategy: you keep on multiplying that same base root, so to speak, that same thing you saw, until it can cancel. Now for square roots, you only need to multiply things twice in order to cancel. That's why they're called square roots, or two roots, right? There's an invisible 2 in front of this root. So once you multiply 2 of them together, you know your roots will cancel. And I'm saying that very explicitly for this third example. Let's keep going. Up next, the idea here is to realize that this is really just root 2 over root 3. And so after I write that, I can say, oh, okay, I need to once again multiply by something to get rid of that bottom root. Now what I want you to notice is what I've done in both examples is I've always multiplied by, again, 1. I multiplied by the same thing on top as what's on bottom, so that this whole thing is worth 1, so that this ugly thing times 1, with my very particular choice of 1, does not change the value of my root, but it changes the appearance of my root. Okay, so what happens? I end up with root 6 over root 9, but of course, root 6 doesn't work out, but root 9 does, and I'm good to go. Now, one other thing we need to say real quick is division on the outside of a root can never interfere with the number on the inside of a root. So in other words, it's very tempting to see a 5 over 5 and want to reduce. It's very tempting to see a 6 over 3 and want to make 2. But you cannot not do that at all if one number is on the inside of the root and another number is on the outside of a root. Just be aware of that. So this is your fully simplified form so far. Okay, next. The whole idea here is let's really figure out what it means to be able to cancel a root, and it's kind of small font, so we'll do it a little bigger. So to cancel a root, let's see if I still do my regular procedure. I multiply root 3. I multiply, cube root 3. I'm multiplying by 1, same thing on top as it is on bottom. Let's see what happens. I get a 5 cube root 3 over, I guess now I've got a 9 cube root 3. But here's the trouble. 9 is not a perfect cube yet. So what do I do now? Well, I multiply another cube root 3, another one of those base roots, so to speak, another of those things I originally saw that was a problem. So notice that. I multiplied one of them, so now cumulatively there's 2 on the bottom. But I'm not trying to make 2, I'm trying to make 3. There's a cube root down here, so I'm multiplying it once again. So I went from 1, multiplied another and got 2. I'm at 2, but I needed to multiply another to get 3. Let's see what happens now. I've got 5 cube roots of 9 because the inside contents come together. I've got a cube root 27 because the inside contents come together. And finally, that means I have 5 cube root 9 over just 3, and I'm done. Again, 9 over 3, don't be tempted to reduce because the 3 is on the outside, the 9 is on the inside. They are safe, and they are not like one another. So that would be our simplified answer. Now, one thing is, in most mathematical cases, when we say the word simplified, it usually means we had to write less. So that's the one very interesting thing about rationalizing, is that when you rationalize, often, I don't want to say often, but usually you almost end up with needing to write more than you originally had, right? This almost looks simpler than what I have here, but according to mathematicians, this is the better simplified form, and that's really what we're investigating. Okay, up next, what are we going to deal with? Well, we're going to deal with what if your denominator has more than one term and one of them is a root, or maybe both of them are roots. But what do we more specifically do when we have more than one term? And so the issue here is, and maybe we'll just write it out for a little bit. Normally you would think, oh, well, what I'm going to do here is I'm going to multiply just root 3 and root 3. But the issue is, yes, this will cancel, but this will just make 5 root 3, and so you haven't gotten rid of your root. So just multiplying one simple little thing, one copy of the root that's a problem, isn't going to do it. But the good news is we have learned a term over the course of this course that will help us, and it's the conjugate. We're going to take that denominator that has at least one part that's a root, and we're going to switch the sign in the middle. And this will be how we get rid of the roots. Let's see how. So first in the numerator, 7 times root 3 will actually just be 7 root 3. They don't kind of come together, so to speak, but they multiply to one another outside and inside. Then 7 and negative 5 make negative 35. On the bottom, let's see what happens. Root 3 will make root 9 because the insides will multiply. Then I get a negative 5 root 3. Then I get a positive 5 root 3 from the foiling process. And then I get a negative 25. Okay, so why is that so special? Well, let's see. Now I've got my 7 root 3. But let's look at the denominator now. That's just 3 because 9 square roots. These cancel, and I have negative 3. Or negative 25. So now I have 7 root 3 minus 35 over negative 22 when I deal with those. Oops, sorry, I know that got cut off, my bad. So let's just review that again. We foiled root 3 is root 9. Positive root 3, negative 5 is, well, negative 5 root 3. Positive 5 and positive root 3 is positive 5 root 3. 5 and negative 5 is negative 25. That's that foiling there. So again, what happened, root 9 is 3. The outer and inner, the O and I of the FOIL cancel. That's why we call these conjugate pairs, because of that special behavior that the middle terms will always cancel. And then we have a negative 25 at the end from the 5 and negative 5. From there, the numerator just stayed because those couldn't combine, but I got negative 22, and I'm almost done, but let's say it this way, just like this whole, sorry, let me zoom out, just like everything we've done is because we shouldn't have a root in our final answer, we shouldn't have a negative on the bottom in our final answer, sorry, we shouldn't have a root in the denominator of our final answer. Similarly, we shouldn't have a negative in the denominator of our final answer. Now, the thing to do with that is actually really simple. We just multiply -1 everywhere, change the sign of everything, and we're good. All right. So for this next one, we'll go through it. I almost, I want to be lazy and skip it, but I won't, because after all, we should review all of it. Okay, so our conjugate is just take the same thing but switch the sign in between. Now I know this looks really, really funky. You might be thinking, well, you can almost confuse yourself. Why is this on the bottom but I didn't switch the sign of this? Because remember, although this looks totally wacky, this is really blah over blah, so this really is just 1. It always needs to be 1. We always need to multiply by 1. We can only change the appearance but not the worth of the problem we're dealing with. Okay, let's FOIL that out and see what happens. 12 on the outside with a root 5 and a root 11 will be 12 root 55. 12 on the outside with a root 3 will be 12 on the outside and root 15 because the inside contents will multiply. On the bottom, we have root 121. I'm just going to say this, the outer and inner will cancel. I'm going to be a little lazy there. And I'll have a negative on the outside, root 9 on the inside, because there's a negative and a positive sign here. So there is a negative that comes out of the multiplication, but it's not inside the root, it's on the outside of the root. And 3 times 3 is 9 on the inside of the root. I'm skipping this middle because, again, I almost want to say it this way. This is a vocab term. When you see same thing with sign switched, you should be saying, oh, that's vocab. I know the middles will cancel because that's why we give this the name conjugate pairs. Okay, from there, we've got 12 root 55. We've got 12 root 15. And this is, of course, over 11 minus 3 after I deal with those roots. And, oh man, just when you think you're done, you're not. So what this is this is going to be 12 root 55 plus 12, whoops. This is going to be 12 root 55 plus 12 root 15 over 8. But here's the issue, and here's why I'm not done yet. 12 on the outside, 12 on the outside, 8 on the outside can all be reduced by 4, so this will be my final answer. And that's just, honestly, I guess I want to say kind of annoying. They have to go through all those steps. But you need to make sure your outer numbers are reduced fully. Again, those outer numbers did not touch the inside that we were working on. So there we go. All right, that leads us right into 8.6. For 8.6, the name of the game is isolate a root, then raise to remove the root, and then I'm going to say quote-unquote solve. But the big thing about 8.6 is extraneous solutions are possible. So for whatever answer you get, you need to plug it back into the original and make sure it's valid. Okay, so again, the first step is isolate a root. Well, there already is root isolated, so we're going to square both sides. When I do, squaring a square root cancels, and squaring 6 gets me 36, and so I get x equals 41. Now, what I'm going to do for sake of time is skip over this, but you should plug in 41 and prove why that works. You do need to check your work through these problems. Up next, I've got a cube root isolated, and so I'm going to cube both sides. Cubing a cube root cancels, and cubing -2 gets you -8. Careful when you're cubing, the negative can end up staying. And so from there, we have 3x equals negative 9. When I subtract that 1 over, I have x equals negative 3. And I'm going to put a box around it because, again, I've already plugged this in and verified that it works, but you need to plug it in yourself and verify why that works. And now we get into the more nasty sections. Up next, we do have a square root isolated on the right. So I guess what I want to say here is that on the left, this is not an isolated root. There's more than one thing here. But because one side, the left or the right, has an isolated root, you are good to start squaring. Now also, because this is one term, when I square both sides, I don't need to FOIL here, and that will be different for the next example, just saying that out loud. But I can actually square and get 16 here and get just x here, and I can just get x plus 60 over here. So I squared both sides. Because this was one term, I could apply the square to each part and move on. Okay, well, all I need to do there is subtract the x. So I get 15x equals 60. And so I get x equals 4. And once again, I've plugged that in and verified that it does work, but you should do that for yourself. All right, now we get to something interesting. So now the idea is, and we're going to formally write it out, but I know we did in the notes together. We're going to say there is an isolated root, so I am squaring both sides, so let's see what happens. On the left, I do have x plus 7, but on the right, I do have x minus 5 times x minus 5. That's what it means to square. You multiply something by itself. And that means this ends up foiling out and giving you x squared minus 10x plus 25. I'm kind of rushing through that foiling because that should be reviewed in known concepts, but that's where we find ourselves now, is that I did square x minus 5, and this is the algebra I got. Now the other thing is that now we need to solve this, and because there's now an exponent of essentially more than 1, or because I see an exponent, the only strategy we know in this course is to move everything over to one side so that we set one side equal to 0, and we're going to factor. So if I subtract the x, and if I subtract the 7, let's see what happens. I have x squared minus 11x plus 18 equals 0. That's what happens when I subtract the x and I subtract the 7. From there, I need to factor, which again we're going to do quick because that should be review. The factors of 18 that add to 11 are 9 and 2. They'll both need to be negative to get you that negative 11 in the middle. But then, of course, you need to solve each of those, and some of those are simple and we can kind of quickly go through them, but you'll end up getting 9 and 2. Now, here's where it becomes super important that you plug the answer back in and you ensure that it works in the original. So, let's deal with 9. I'm going to do 9 on the top here. On the top, if I plug in 9, that's 9 minus 5. And on the top, if I plug in 9, that's 9 plus 7. That's 4 equals the root of 16. And that's true, so 9 is a true solution. I guess a little underneath, I'll deal with 2. So 2 minus 5 should be equal to the square root of 2 plus 7. But that's negative 3 over here is equal to the square root of 9. And that's not true. So 2 is extraneous, but 9 was the true solution. So now we see that there is a reason that we say we do need to plug our answer back in and ensure that it actually works in the original. Okay, let's keep on going and see what we get now. First step is I need to subtract 3, which will get me negative 2. I was thinking ahead. No, equals positive 2. Sorry, excuse me. And now that I've moved over that 3, I now have an isolated fourth root. If I raise everything to the fourth, then that's going to be just x plus 3 because I raised it and canceled it. And 2 to the fourth is 16. And so all I need to do now is subtract the 3 and get 13. And we're good.